Hello ladies and gentlemen, great to see you again. Thanks for tuning in today for what is the 14th lecture of GGS 300 Quantitative Methods for Spatial Science. Today we're going to be covering regression, and we're getting to a really exciting part of the course because we are closing off a lot of the work that we've done over the past term. This is the last taught lecture and the last laboratory, and we're getting on to one of the most exciting topics and widely used topics within statistics, and that is regression. So where are we at in terms of the course? We have some assignments still due, we have the exam still due. So essentially there is an assignment that is due this week, so that will have been correlation, and then you have the final assignment which is due on December the 11th, so the following week, and then we'll have the final exam by December 15th. So we finish all of the taught methods, all of the taught course this week, and then we have a reading week where you'll have time to prepare for the exam, to cover any of the final assignments, and then we'll be done, ready for the holidays. Fantastic. Let me know if you've got any questions. You know I like hearing from you, especially if you've got good feedback. So please reach out to me if something isn't clear, or if you have any questions around the exams or the coursework. I'm always available to chat. So I've mentioned already that we're going to do regression today, and then we've got the exams. I think that's fairly clear to you now, so it's not a very complicated end. So let's get on with the content. And really, we're kind of wrapping this up now. So the first part of the course, obviously, we focused on the descriptive statistics part, and now we're focusing very much on testing hypotheses and evaluating hypotheses. And what's great about this is that by the time we get to the content today, we're going to be able to understand things like multivariate regression. So what that means is where you have multiple input data factors which can help to explain a single output factor. And whereas a lot of the previous tests that we've done have been bivariate or univariate, so using a single or just two metrics, here we can get into really much more complicated modeling approaches, and that's good because the world's complicated. If we want to understand how factors may influence certain geographical variables, you may need more than one or two explanatory factors. You probably will need 3 or 4 on a standard problem. That's the kind of strength of what we're going to be covering today. And we've worked our way through the flowchart now of common statistical tests. So we've been over to look at discrete and categorical tests. We've done lots of difference and difference tests for both parametric and non-parametric approaches. And we've also focused on correlations. Today we're going to be focusing on regression modeling. So just before we begin, I just actually wanted to go back to the very purpose of why we do statistical modeling. And actually, I was looking through a textbook that I used a number of years ago. It's actually very good, but it's a bit off topic for what we're doing. It's actually by Andy Field, so I've just got a copy of it here. And what I liked about it when I was just doing some background reading was that he kind of boils it down to this. This is the basis of statistics: the fact that you have some outcome, some data outcome that you want to understand, and then you basically fit a model, and this is the amount of explainable data variance that you're able to capture in your model. So you're able to say that the variable or variables that I've included here explain X percentage of the change in this outcome variable over here. And then the unexplained variance falls into this error term over here. Okay, now this is just pretty much the basis of all statistics. So I just wanted to emphasize that before we get to regression, this is how you kind of need to think about the world. And if you're able to understand this and understand how we apply that, then you'll have grasped a really important concept from this entire class. And essentially what that means is, I kind of broke it down before. We have the explained variance in the model here, which is the numerator, and we have the variance that we can't explain via the model, so effect and error, and that gives us basically a test statistic for that model that we're fitting. So this is a very simple way for us to kind of understand, in the simplest possible terms, kind of how we're approaching the problem and the types of ways that we evaluate the problem. So now let's get on to simple linear regression using least squares approaches, essentially. So what's the kind of form and nature of the relationship between the variables that we're interested in studying? So let's say we're interested in house prices again, we're interested in those factors which affect house prices. And we can build a regression model which, for a particular we can put in building dimensions, we can put in floor area, we can put in a variable for whether a house has a garden, and all of these will influence the potential price that we think the house is worth. And we're able to do that type of equation in this approach by using regression, because we're able to input lots of factors, explanatory variables, which are able to explain the main variable of interest here, which is price. Okay, so this is where we are moving away from correlation to look at these kind of more causal ways to interpret the world, and this is a key statistical tool to do that. So as I say, correlation, as we focused in the previous lecture, focuses on kind of the strength and the direction of relationships between two variables, whereas in regression, we're really moving towards a functional relationship across many different variables, if that's what we're interested in. So both correlation and regression are measures of association between the variables, but correlation only measures the strength and direction, whereas regression is able to focus more on potential causal relationships. Now, I'm always a bit hesitant about using the word causal because it's very hard to actually prove causality. So we go back to that original adage I mentioned before, which is, correlation and causation are two different things. So we need to be somewhat careful here, but regression approaches provide you with much more insight into potential causal relationships, and that's why this is a kind of a much stronger way to start to understand how the world works. So in regression, what you need to do is you need to specify an output variable. So let's say that's price, which would be y, a dependent variable, and then you need to specify a bunch of explanatory variables which are independent of this, which we think drives the output variable, which could be those factors which we think affect house prices. So it could be the number of bedrooms a house has, it could be the floor area, it could be whether it has a swimming pool, it could be the size of the garden. So this is the type of thing that we're able to do and will do in this particular lecture today. So regression analysis explores the quantitative relationships between variables when one or a few variables influence or affect one another. And I'm going to keep coming back to this concept of dependent and independent variables because it's something that I'm afraid you're just going to have to learn, and it's a useful way to then start thinking about the world. So the dependent variable is what we think is receiving influence or effect, such as the house price, and the independent variables are what we perceive as the variables which are creating that effect, such as the size of a property, or the factors which we think are attractive for people to pay more in a market for a property. So that's the independent variables. So there's plenty of examples, that could be looking at the income of people based on how many years of education they've had. So maybe if you've only had a few years of education, you might not earn as much as someone who's had 20 years of education, who therefore commands a much larger income in a job market. We could look at the yield in agricultural fields based on the amount of fertilizer that's being used. So we could expect that if you only use a small amount of fertilizer, your yield at harvest time would be much smaller, whereas if you use a lot of fertilizer, you could expect that your yield would be much larger. We could expect that altitude and rainfall are related in that way. So maybe at higher altitude, we would expect higher rainfall. And we could also look at land values in relation to the distance from city centres or the quality of a neighbourhood. So this is quite similar to the house price example that I gave you. Here we could be saying, well, what's the price of a piece of land? And then what we could do is we could measure the distance for that parcel of land. We could take the centroid to the centroid in the city centre, or the downtown area, and then basically use that as a distance measure, which we could put into the regression. We assume that if If the distance is smaller, there will be a higher price because there's greater competition for space. And then in terms of quality of neighborhood, maybe what we could do is we could place variables in there which reflect the neighborhood. So maybe we put in the crime rate. Maybe areas with low crime have a higher land value. Maybe we could put in the socioeconomic status of the neighborhood. So that could be median income, or it could be the number of individuals in that neighborhood, the percentage of individuals in that neighborhood that have a tertiary level education, so a college degree basically, a college degree or higher. And these are the types of variables that we standardly put into those regression analyses when we're interested in doing that type of urban and regional economics activity. So I used to be in urban and regional economics, and we used to build a lot of these regression models. Okay, so just think of the independent variables as explanatory variables and think of the dependent variables as being dependent on the explanatory variables. I hope that that's clear now. We've been over it a number of times, and we'll be able to go over that in greater detail when we get through to the lab, and then you're able to kind of understand the structure of the equations. So what we're doing is we're hypothesizing that the dependent variable, i.e. house price, is influenced by the independent explanatory variables. So all of those other things that we think predict house price. but that's very good, because that means that ultimately once we've fitted that relationship, we're able to extract a line of best fit, for example, through the data points. We can use that to predict what the house price may be in other areas where we don't have data. So if we have the predictors, we can then use the slope of the line that we obtain to then predict what the price may be in unknown areas where we don't have data. Okay, so the first thing that we need to do when we get some data and we're interested in doing regression is we need to understand the relationships between the data, and that means we need to scatter plot it. So I explained to you before about when I was doing my PhD, and I saw that a much older and much more experienced researcher starting out on a new area and basically developing like huge numbers of correlation plots, so to understand how all these different variables are correlated with each other so that he could start to understand a problem. And that had a really long-lasting impact on me, because you may think, oh, correlation is such a simple concept, but it's kind of the fundamental way when you visualize things to understand how certain factors are related to others. And that's really important. So even if we move on to more complex techniques, we should always start by scatter plotting the data, and we will do that when we get to the laboratory session today. So bivariate linear regression, let's just start with a single dependent variable, and let's start with a single explanatory variable. So we just have two variables here. It's the simplest type of regression model that we can basically build, and it's based on trying to define a linear functional relationship between these two variables. So the question that we have here, for example, is there a linear relationship between the number of years of education and the income which someone is able to command on the job market? And the way that we do that is we have a y value, which is the dependent variable. So in this case, that's income. So here we go, we have it on the y-axis. And then we have an x variable. So that's on the x-axis here, which is number of years of education. And we have b, which is the coefficient, which basically reflects the slope. So this line has a particular slope that we fitted to the data, and that b reflects that. And then we have an a value, which is the intercept of the line. So that's where the line passes on that's where the line crosses the y-axis. Okay, so we have y equals a plus bx. Okay, and a and b are constants in this case. And then we have the y and the x, which reflects our data variables. Okay, so the way to kind of understand this is that for every one increase in the x-axis, so in this case a year of education, we have a certain increase on the y-axis, so that's the income level. And what we're trying to find out when we've got these two data points is what that n value is essentially, and that's how we start to understand the relationship, the linear relationship between these two variables when we're able to estimate that slope parameter n. Okay, so least squares regression. We need to start to estimate those values of a and b, and this is something that we will do by hand when we get to the laboratory session. And the way to do that is to focus on a least squares approach, which is basically it's a line of best fit. So we're regressing one variable against another in order to develop this line of best fit. And it's the estimate of the relationship, the best estimate of the relationship between the two variables. And that can serve as a predictive model, which is great because we want to be able to have that predictive capability within our statistical toolbox. And that's something that, if you can get into predictive analytics, then that's a really fantastic area to be in. But all of that predictive analytics area is dependent on this kind of basic statistical information that you've learned within this class. So I would thoroughly recommend you thinking over the long term about how you can move into that area. I was advised to move into that area, for example, when I finished my PhD, and that was 6 years ago now. And I think that was really great advice because there's just so much capability in that area. It's you get better job conditions, better pay, potentially get interesting problems to work on. So I would very much encourage you as well to think about how you could do predictive modeling. And we're going to do that in the lab, actually. We're going to produce a very simple example of how we predict a y metric, so an outcome variable given an input variable such as a value of x. So I think that this is exciting, and you should definitely put thought into how you can further your career in this area and think about potentially doing it for your dissertation. So if you've got a research paper that you have to write or a thesis that you have to write, definitely think about trying to apply this approach. Okay, so the actual line of best fit that we're talking about is one that essentially minimizes the sum of the squared vertical distances between each point and the line. And this is going to be a key concept which we're going to keep coming back to within this lecture, because that value between the point and the line also forms the kind of residual, and that's very important for us to understand how well the model fits reality, or doesn't, as the case may be. So we will cover quite a bit of distance on this today. So the least squares regression, so for a specified candidate line, and we've already covered this regression equation, so that's y, our output variable, equals a, the intercept, plus b, so the slope coefficient, multiplied by x, which is the x value, so that the explanatory variable. So for a given value of xi, we can calculate that the corresponding y hat I value is a certain magnitude. So we're able to get a predicted value. And the point is that the least squares approach, which I'm talking about here, which we mentioned previously, which minimizes the distance between all of the points, is minimizing this quantity here. So essentially, this is important. This graph just here, we've got the x variable on the x-axis, we've got the y variable on the y-axis. And what it's doing is we have all of these points, so 1, 2, 3, 4, 5, 6, 7. Essentially, it's minimizing D1, D2, D3, D4, D5, D6, D7. And this is the line which it eventually estimates based on minimizing that particular function, okay? So it's minimizing the distance between each of those points. Great. And these look pretty scary equations, and we will calculate them within the laboratory. Obviously, the key point is that once you know how this is done, you can just use the input function, and that's what everyone uses on a day-to-day basis to run their regressions. But the important point is you need to know how to calculate it by hand before you progress to using the inbuilt statistical software. So to get the beta coefficient, the beta coefficient, you basically need to run your data through this equation in order to obtain it. So you need to get the summation of x multiplied by y minus the summation of x times the summation of y to get the numerator, and then you basically need to get the sum of the squared x values and then subtract the sum of the x values squared in order to obtain that beta coefficient. And for the alpha intercept, we need to get the sum of the y values and subtract the sum of the x values multiplied by the beta value for the numerator, and then we need to divide it by the number of samples that we have. So don't worry if this looks intimidating, we will cover it and we'll go over it nice and slowly, and you'll have the code as well as the math. And actually in the exams, I'm not going to ask you to calculate this by hand. I will let you use the inbuilt function in order to produce the results. So what I'm really looking for you to do here is to be able to think, this is the problem where I'm going to apply this test. Do the data fit the assumptions for the test? Yes, they do. Can I run that test and then extract the important part of the information and explain it in a sensible way? That's what I'm looking for you to do. I'm not looking for you to do some complicated math, okay? And when we run through that equation, we're able to get this type of line of best fit that we are interested in. So there are other ways to calculate those values, and we do calculate those values in the book in that way, but we are also able to calculate it in a different way. So to get the alpha, the intercept, we're able to take the mean of y and subtract the beta multiplied by the mean of x. And to get the beta coefficient, the beta coefficient, we could also take the correlation coefficient and multiply it by the standard deviation of y divided by the standard deviation of x. And actually that will give us the same results. It's just much simpler to understand, which is great because I like simple approaches, and I'm sure you do too. So as I've already mentioned, A is the intercept, so expect a value of y, so the expected value of y when x equals 0, and the slope, so that's the regression coefficient. It can be referred to, it can be the beta coefficient, but just think of this as the quantity by which, if you increase x by 1, then this is the quantity by which y will increase. So we'll cover that when we get further on, so don't worry if that seems daunting. We will go over this many times so that it's clear to you. So it shows the absolute change in y associated with an increase of 1 in x, as I just mentioned. And it shows the direction of the relationship. So this coefficient, the hint is it's a coefficient, it runs from -1 to 1. So if it's positive, it's going to indicate that it's a positive correlation. If it's negative, then it's going to indicate that it's a negative correlation. And if it's 0, then it's going to indicate that there's no relationship between the two. It's just a flat line. Okay, let's have a look what we've got here. So yeah, I think that this is fairly standard stuff. So the prediction should only be done in the range of x values. The coefficient signifies how much the mean of the dependent variable changes given a 1 unit shift in the independent variable while holding all other variables in the model constant. I think that that's pretty key. So in economics, they have this phrase ceteris paribus, which is just holding all other things equal, which is kind of an abstract Latin phrase for what we've got here. So I don't really want to get into it, but this is pretty common way to understand how the world works, and that's the beauty of it. It's saying, there's all this complexity. We're going to hold all of those variables still and just vary one variable at a time and see how much variance that causes in another output variable. And that's a really important way to be able to understand the world, because you want to understand the effect of different explanatory variables and the quantity of those the quantity of the variance explained by just one or two or a variable on its own is really important. That's the fundamental kind of driver for this approach, and you want to look for the model that best explains your data in as few variables as possible. So this is, called elegance within the statistical modeling sphere. So people will say that an elegant model is one that has, just a very few number of variables, but explains a very large amount of the data variability. So, the classic one is in Newtonian physics. If you look at the gravity equation, you've got three individual data inputs, and so you've got the mass of two different objects and then the distance, and then you've got a gravitational constant. So in reality, you've just got three input variables there for the mass of the two objects and the distance, and that's able to predict the force of the gravity, and that's really simple. That can explain probably about 80%, if not higher, of the variance in data, if you were to look at that in this way. And that's what really kind of what we want to do. I would say that it's quite hard to get to that level of statistical power in the social sciences, particularly in this area if we're thinking about kind of the social geographic aspects, because people change their behavior and kind of society is much more messy than a predictable physics-based equation. But this is kind of the essence of what we're doing, and I think that's an important example. We want to find a very simple model which explains as much variance as possible. Okay, so we can progress from here, and let's start to think about bivariate regression analysis, actually trying to use this method inferentially. So how do we actually apply this in order to understand the world? And you'll recognize this fairly standard layout that I've got here for how all of the tests have been laid out. So the objective here is to determine if X accounts for a significant proportion of the variation in Y. So our explanatory variable depends a significant proportion of the variation in our dependent outcome variable. So how does years of education affect income of people in the labour market? Or how does the size of a plot of land affect the price which you might pay for it in a property market? There are requirements. There are quite a lot of requirements, and actually, this is the thing that always causes the nightmare, because you have to make sure that your data fit the assumptions for the regression approach. So for this kind of methodological approach, and there are quite a lot of assumptions for regression, and we need to make sure that we adhere to them. And we'll have to do quite a bit of work today to go over what those aspects are. So we basically require that there are two randomly collected samples, that there is a linear relationship between the predictor variable and the outcome variable, so between X and Y. We expect that there's normality in the error residuals. So remember I mentioned before that the residuals are the distance between each of the data points in the model and the line of best fit that we fitted. We're looking for those residual values to be normally distributed, so Gaussian, parametric, and we've covered that before in the previous lectures for how we test for whether there is normality in a data distribution. We're interested in there being equal or constant variance in the residual errors. So that's again focusing on the residuals, but we want to make sure that if there's variation, then that's kind of randomly distributed variation, and then it's equal across the predicted values. We don't want to see kind of funky distributions of those errors when we plot them, because that would indicate that the variance isn't equal, and that starts to jeopardize the results that we produce. And we want the residuals to be independent, so we'll cover this as we move on. And this is specifically focusing on ratio or interval based, so continuous based data metrics. So the hypotheses, so we have a rho squared here. So the null hypothesis is equal to 0. So we're saying that there isn't any significant difference, whereas the alternative hypothesis here is that there is a significant difference. Okay, and we use the test in order to test these hypotheses that we're going to produce. So what are we going to do to get the f? Well, we can use this equation just here. So we can take the coefficient of determination, which we haven't covered yet, but which we will cover. So we covered the correlation coefficient previously, and it's very similar to that. So essentially, we need to take the coefficient of determination, multiply it by the number of samples minus 2. So essentially, so that's the numerator. And then we need to get the denominator, which is 1 minus the coefficient of determination. We can get the coefficient of determination over here. So if we sum up all of the explained variation in y, and we divide it by the sum of the of all variation, then we're able to get the coefficient of determination. So this is how good a predictor, how much data variance you are basically able to explain within the model which you fitted. And there is an issue around how you get the number of degrees of freedom for the model, and this is going to matter, when you test the probability of your F statistic occurring. You'll remember in R that we need to specify how many degrees of freedom we have, and essentially we do that. So we have the degrees of freedom based on the number of predictors in the model. So you're going to have fewer degrees of freedom if you have fewer, as you increase the number of explanatory variables in your model, you're going to need to reflect that within the number of degrees of freedom. And you need to get both of these numbers of degrees of freedom here, so DFN and DFD. So this is the number of observations that we have in the sample minus the number of predictors that we have in the model minus 1 in order to get this. Okay, so don't worry too much about these now. We will get to this in the laboratory when we need to test the probability of that F statistic occurring once we've obtained it. For now, just worry about how we produce these metrics here, which I will go over once we get into the laboratory in greater detail. So you'll remember at the beginning I explained that the basis of statistics is that we have some outcome variable, and then we basically say that we have explained variance for a model that we can fit, and then we have the unexplained variance, which is the error. And that's the basis for statistics, and I'm reflecting that here. So we have data which equals some sort of fit plus a residual, and that means that we end up with these types of data metrics which we're going to need to use when we need to do some calculations. So to get the total variation in the data, we get the total sum of squares, and that basically is equal to the regression sum of squares. So that's all of the explained variance that we have within the model that we fitted, and then we have all of the unexplained variance, which is basically the error, residual, unexplained sum of squares, so the ESS. So to get the total sum of squares, we basically need to add together the RSS, the regression sum of squares, with the error sum of squares. Okay, so we will do this as we move forward, and we have the equations down here for how we're going to do that. Okay. So fit part variation, also called explained variation, is the amount of variation that can be accounted for by the independent variable x. And the fit part for the strength of the model is the RSS. So we've kind of covered all of this already. Residual part variation, so this is essentially all of the unexplained variance. So it's also called the unexplained variation. It's the amount that can't be accounted for by the independent variables that we placed into the model. One thing you might have heard of is omitted variable bias. So this is essentially where you don't include an important explanatory variable, and that can lead to some strange potential outcomes in the regression model. It also may plunge a whole load of the data of the data variation into that unexplained proportion, because you're leaving out a major factor. And we've got a paper which is under submission at the moment, which we just got the reviews back for, and I was pretty concerned that this might be an issue. omitted a variable bias, having spoken to a couple of people since we'd submitted it. We didn't get too many comments back from the reviewers on this, but the problem always within kind of spatial science when you're working on this at a local level is that you might not have the data that you need at that level of spatial disaggregation. So if I said to you that we wanted to build a model at the census tract level in the US, perhaps we want to build one for Virginia State, we might not have a lot of the data that we need to put into the model at the census tract level because it's so spatially disaggregated. So you kind of have this tension of, I'm a spatial scientist, I want to build a regression model that reflects spatial processes. But then if you don't have the data, it can cause a lot of problems in how you kind of fit those models and build those models. So this is a key part, essentially, of kind of how you recognize and evaluate the ability of your model to actually predict the dependent variable of interest. And I've just emphasized here that the residuals are the observed response minus the predicted response that we get, and I'll return back to this at a variety of points when we start to do the residual analysis. Oh, and just one more thing, the mean of the residuals is 0 because we're going to be looking at those distances above and below the line. So we would expect if the data are normally distributed, that the residuals are normally distributed, that the mean of the residuals would be 0. So the coefficient of determination I mentioned previously when we were covering how to get the F statistic. And essentially this coefficient of determination measures the strength of a regression relationship. It's not tied to measurement units, and often it can be transferred into the percentage of variation that's explained by the independent variable. I've got a paper that I might share with you which focuses on trying to predict income levels from satellite imagery, and this is exactly the approach that we've used. We explain the model in terms of the percentage of the variation that we're able to explain based on essentially using satellite imagery to try and predict on the ground conditions, and we applied that to Malawi and Ethiopia, and we think that this is a really fun project to work on. And this is kind of a good example of how we would apply this type of statistic in a real piece of research. So don't be put off by some of the big equations in here. This can be applied to so many different things, and it can be used in very cutting edge research. So definitely stick with trying to understand this content, because it will definitely put you in a good place for how you progress after this course. So the coefficient of determination exists between 0 and 1. So if you had 1, it would be a perfect fit. If you had 0, there'd be no relationship between the variables. And we get the coefficient of determination by taking the regression sum of squares and the total sum of squares. So this is how much variation the model explains, and this is how much total variation we have in the model. So we did cover this previously. I just placed it down here in the bottom right hand corner of the slide, and it's expressed slightly differently mathematically, but it's exactly the same way to calculate it, essentially. So just remember, it's a ratio of the explained variance over the total variance. So what does a regression output look like? And I think I always used to think that this was scary stuff when I first started, especially as you're running the code on the command line, it's printing it out to the console. It's quite a big step up. What I do want to say though is don't be discouraged by this type of approach, because I was using graphical user interface based statistical technology until I was about 25, 26. So the fact that you're learning this now is really fantastic, and it kind of signifies how much the world has changed in statistics over the past kind of 10 or 15 years. And now we're moving towards much more advanced things at an earlier age, and I think that's a fantastic opportunity for you. So what does it produce? Well, essentially, this is the regression output over here. So we get the distribution of the residuals. So we get the minimum value of the residual, the maximum value of the residual, then we get the quantiles, and then we get the median value. So we're looking for something that isn't massively skewed, essentially. So this is reasonably well normally distributed. So you can look at the minimum and the maximum, and they're roughly the same above and below the mean value. in a normally distributed data set, our median and the mean would be both 0, and this is quite close actually. And there's not too much, in fact, these quantiles are actually very similar to each other. There's very little variation between the two. So these residuals actually are really quite normally distributed, I suspect. And I don't think that if you were to test that with a Kolmogorov-Smirnov or the Shapiro-Wilks test, that it would be significantly different from the normal distribution. So I suspect that this is, fairly good at meeting the regression assumptions required for this test. So that's the residuals. So don't be too scared by that. We've seen this before. It's just a descriptive statistical output for how the values vary around that line of best fit that we fitted. Coefficients. So this looks big and scary. I think the first thing to say is just don't worry about this significant code thing here. This is just literally saying that if the p-value is 0, then it will get 3 asterisks. If the p-value is below 0.01, it will get 2 asterisks. If it's below 0.01, it'll get 1 asterisk. If it's below 0.05, it will get a full stop. And if it's below 0.1, it will not get anything. So the point is that this is just the same output every time you run the test. It's just giving you an indication as to what these things are going to mean here next to the p-values. And then what we have are 4 different columns. So we have the estimated coefficient here. We then have the standard error here in this column. And then we have the t-value. And then we have the p-value, so the probability of occurrence. So essentially, where do we start? Well, remember, this is the coefficient and this is the error. So actually, the t-value is just the ratio of this divided by this. So if you basically divide this here, so let's do that. If I take 9.5 and divide it by 0.92, I get 10.32, which is essentially this value here, 10.26, if you include all of the additional significant figures, which I didn't. So this t-value is just the test statistic, which is the ratio of the explained variance to the unexplained variance. Okay, and then all we have here is the p-value. So it's just saying, well, if this is the test statistic, give me the probability that that's occurred by chance. So in R, we would just use a quantile lookup, and it will give you a p-value. And here for the x1 variable, this is highly significant. So there's a highly significant impact of this variable on the main output variable y, and we can be more than 95% certain that this hasn't just occurred by chance. So that explains these different columns here. And then obviously I haven't really spoken about the rows yet, so I just need to do that briefly. The intercept is your alpha value. It's where the line crosses the y-axis essentially. So that is at 4.6. The significance level doesn't really matter for this because all you're doing is considering the slope of the line. And then you've got your independent variable, your beta coefficient here, where the significance level does matter. And this is providing you with the test statistic, the standard error, the t-value, and the probability for that variable. So I hope that that's given you a bit of an explanation for the coefficients. I hope I didn't go over it too quickly for you, but we will go over it in the class so you'll have a bit more of an understanding. So what I've done is I've broken down this into the residual distribution, which is fairly simple to understand. We've covered that before. The coefficients for the model, which is not that different from what we've covered before. It's just that it's a lot of text that's outputted here, but you get all of the metrics of interest in one place, which is nice. And then what we have down here are the actual model test statistics. So we have the residual standard error based on the number of degrees of freedom. We have the multiple r² value and an adjusted r² value. So the difference between these are just that the r² value, which it gives you an understanding of the explained variability, that basically inflates as you include many variables. So actually you have an adjusted R-squared value which tries to correct for the number of variables which you've placed into the model. And this is just saying, 53 or 54% of the data variance in Y is explained by the model that we've produced. And the F statistic is the test statistic that for the overall model, which we discussed before, given the number of degrees of freedom. And we've got a p-value for the overall model, and it's highly significant. So we think that there's a significant effect of X on Y, given this particular model that we've got here. So there's a lot of text around the outside here, and basically it's just talking about all the things that I've already spoken to you about. So I don't want to go back through it in detail. You can either rewatch the video or you can read this through as you like. But this will give you a good understanding of kind of what you should be looking for in this output. And I think importantly, I just want to give you confidence not to be scared and intimidated by the results that you've got out of the console. So the residual analysis, and I explained to you before that this was something which we're going to come back to. So the residuals are the amount of deviation that we have from the regression line. We need to make sure that these residuals actually fulfill the assumptions of the regression-based approach. So this is just a brief example here. On the x-axis, we have the distance from a lake, which is over, 0 all the way up to 20 miles from the lake. And then we have the level of snowfall, so 80 inches down here, 100 inches down here. And what we have is a negative correlation. So basically, as the distance from the lake increases, the amount of snowfall actually decreases. And I think logically that makes sense because water has a high heat capacity. So if you're closer to the lake, then that's going to suck up the heat, that's going to lower the temperature, and therefore you're more likely to have snowfall essentially because the temperatures will be getting below 0. I know that's definitely the case, having visited some of those places around the Great Lakes in the winter period, particularly Chicago, Toronto, Columbus, Ohio. They get a lot more rain. That's really the snow belt for that area in the north because of their proximity to the lake. But the point is that we have this line of best fit here. We have the predicted values from our model, which are the orange squares here. So we're saying for 11.4 miles from the lake, we predict that there would be 94.36 inches of snow. And actually the real value is down here. So what we end up with is, for the residual, is minus 8.36. And the way that we got that was we took the real value and we subtracted the predicted value, and it gave us this value here, okay? And then equally for 15.8 miles from the lake, our predicted value was down here at 86.97, and our observed value is actually up here at 96 inches of snow, and therefore we need to subtract them, and when we do, we end up with 9.03 as the residual for this particular data point. So this is how you need to think of the residuals, and we're going to plot them, and it's just the distance from the predicted line value for the model that we fitted. So it's this equation over here. The residual is equal to the actual value of the dependent variable minus the predicted regression line value of y, so y hat. So the assumptions of regression residuals, and I'm afraid there are quite a few, and there's no easy way to shortcut this. You just need to learn them, I'm afraid. So what I would do, and what I did before, was I would just write down all of the assumptions, and I would just I think they call it rote learning. So I would just learn from memory the fact that you have these sets of assumptions that you need to meet in order to run this type of test. And what you need to do when you decide that regression is the right approach for you to take and you run the model is that you need to check that all of these assumptions are met, and you need to report, when you report your statistics, that these assumptions have been met. So we would expect a linearity in the relationships between the relationship between the variables that we are modeling. We would expect that there would be independence in the residuals. So we don't want to see that there's some sort of underlying pattern in the residuals, because it would violate the assumptions that we have within the regression approach. So often this has something to do with time series data. That's one of the factors that we will focus on today. But it could be, it could also be a spatial issue. It could be a spatial autocorrelation issue. But this is something which comes up time and time again, and there's entire people in our faculty and in other kind of spatial science faculties who just build models regression models which try to address those situations where you might not have independence of residuals, so you can attempt to correct for this within the way that you weight your data values. So spatially weighted regression is a good example. And we expect that there's constant variance in the residuals, so we would expect there to be kind of random variance when we plot it. Essentially, we don't want to see this some sort of underlying pattern, and we would expect those residuals to be normally distributed, and we can actually evaluate that by using a QQ plot, which stands for quantile plot, which we will cover shortly. So this is a good example of how we have nonlinearity. So this might be the type of regression output that you get, but the key point is that when we plot the fitted values against the standardized residuals, we get this type of an outcome. So let me just show you why this is an issue. So these are our data points. There we go. And essentially what we have whoops, sorry, this isn't what I really wanted. Okay, that's fine. So essentially what I'm emphasizing is that we have a non-linear pattern which exists within the fitted values when plotted against the standardized residuals. So you can see it decreases down here and then increases, and this is a clear violation of our assumptions, so you need to be aware for that. Over here in the second assumption, so you remember that was focusing on non-independence of the residuals. I mentioned this could be an issue, for example, with time series. So this is actually plotting the the standardized residuals against the time. So this might be the time of the time of collection of the data. So I was thinking, what could be a good example of this? Imagine that I sent you out and I said I want to measure the temperature every 20 minutes. And I wanted you to go out and do it from 5 a.m. in the morning in May. So you still have quite cold nights. And then I want you to do it for 12 hours. So you go from 5 a.m. through to 5 p.m. Perhaps the time of day is influencing the temperature. And that could lead to some sort of correlated outcome with time, which you really would need to, you should really try to reflect in your sampling method. So that might mean that over time you don't have independence of the variables. So as time's increasing here, we actually have the residuals low at the beginning and they start to move high by the end. So you should really be looking for randomly distributed residuals here around the line, and that isn't what we've got. We've got this pattern where it actually looks a bit like a positive correlation, where you could draw a line through there and it would be indicating that there's something else going on, indicating you don't have independence in your data. It's correlated with another metric. So non-constant variance, and in this assumption I need to bring up this idea of skedasticity. Statisticians like to use big words, I'm afraid, so this is just something which you need to get your head around. I think the key part is that skedasticity here relates to the variance within the data. And if you have constant variance, that would normally be addressed as homoskedasticity, or the data being homoskedastic. Whereas if you had non-constant data variance, then that would be called heteroskedasticity or heteroskedastic. So the point here is that you just need to remember skedasticity as the word which relates to variance, and then just use your logic to think about the relevance of those terms to what we're describing. So homo obviously means the same, whereas hetero means different. So homoskedastic is indicative of constant variance, same variance throughout the data, whereas heteroskedastic indicates that there's a difference in the variance that's taking place across the data metrics which you're running a model for. And this, as a consequence, could violate the assumptions within your model. So essentially here, if we look at the standardized residuals plotted against the fitted values, we do get this fanning out of the variance. So we have quite a small amount of data variance here around the line, and as we get down here into the higher fitted values, we actually have lots of data variance around the mean line here. And this is a concern. So you would need to either look at ways that you could correct this. You could look at transformations of your data, but it might not always actually correct for heteroskedasticity. Or you could look at non-parametric data approaches if you weren't able to meet the assumption in this particular area. And then finally, we've got the normality of the residuals. So we want those residuals to be normally distributed. They may not be, and therefore we need to assess this using a quantile plot, which basically compares the theoretical residual quantiles with the actual residual quantiles. So significant deviation from the one-to-one line implies a lack of normality. And actually down here we have quite significant deviation. So we have above the line down here at these lower values, then it crosses over to the other side around the mean, the middle of the distribution, and then it quite significantly deviates above the line as we move to those higher quantiles. And actually, I just found this nice little graphic which gives you a little bit of explanation. So if you had normally distributed data, you would expect those residuals to be basically fully distributed along that line. If you have data that's skewed to the left, which I think we have here, you could expect this effect where essentially you have some above the line and then below and then above as you moved up the line of best fit. And then we could have skewed to the right data. So this just gives you an indication of what it should look like and then some of the other outcomes that you might get. And I've included that because, you know, when I did my statistics course at first, I didn't always get examples from the lecturer of kind of how it should look and how it shouldn't look. And then there's this kind of grey area of, well, what is acceptable and what isn't acceptable. And obviously you can test for this. So we've been through those tests before to inferentially test for normality. So the Kolmogorov-Smirnov test or the Shapiro-Wilks test. Or you can just kind of eyeball it if you're pretty confident that the data residuals that you've got look fairly normal because there's not that much deviation from the line. So what's an example of a good regression? Well, here you can look at the standardized residuals distributed against time, and they're, you know, pretty nicely randomly distributed around here. You can look at the x versus the y values when you plot them on a scatter plot, and this is a nice linear relationship up here. This is a good set of data variables to plot using linear regression. You could then look at the residuals. So if you look at the standardized residuals against the fitted values, these are also nicely distributed. You know, it doesn't indicate that there's some sort of a funky heteroskedastic variation going on. They look quite homoskedastic distributed. So there's kind of constant variance across the data set. And then when we look at the QQ plot at the bottom to look at whether the data points are normally distributed, they look very good. That there's a bit of deviation at the tails from the line, but then when you look through the main part of the distribution, these points are pretty much aligned along that line, so you can have quite a large degree of confidence that these are normally distributed residuals. So I think that provides you now with an overview of the assumptions. I've given you examples of how it shouldn't look, and I've given you some examples of how it should look. And the key point is that you want to kind of learn these by heart, so that if you're questioned on regression, and there will be questions on regression in the test, then you're able to speak in an articulate way about how you meet these and what you should do if they don't meet those particular requirements, some of the issues that might lead to us not meeting those assumptions. So standardized residuals, something which we haven't actually gone into too much detail about yet, but we did use in those previous plots, just allows us to make comparisons between different regressions. So we're able to divide each residual value by the regression standard error to normalize. So there's a rule of thumb: if the standardized residual is below -2 or over 2, it might be an outlier. And obviously, if there's an outlier in your data set, then you might need to make a decision about whether you leave it in the data set or whether you remove it. And this is, again, a bit of a grey area, because it comes down to you as a researcher deciding what you think is sensible based on your questions. So as an example, I had to think about this the other day based on some of the international work that I was doing, trying to look at where 4G and 5G will be deployed globally in the next 10 years. And I had to exclude certain places which had extremely high population density, good examples being the Maldives, Hong Kong, Macau. And that's because the population density is just so high in comparison to some other parts of the world that there is something significantly going on there that's different from everywhere else. And therefore, I made the executive decision that I would remove them from the analysis. You just have to be fully transparent about that in the way you write up the tests, and expect, as ever, that someone might make a critical assessment of your work, and they might review those assumptions that you've made. So you have to have a good reason for why you've rejected or removed those outliers from your data set. Generally, you don't want to be removing too many data points from your data set in case you skew the results. So the standard error of the regression, so the residual standard error, is an index representing the typical distance separating a point from the regression line. Okay, and we've got the error sum squares here as the numerator, and we've got the so we've got n-2, which is quite similar to the number of degrees of freedom potentially, as the denominator, and we take the square root of these in order to get the standardized residual. So multivariate regression. So we basically covered basic linear regression and fitting lines of best fit. Then we've covered bivariate regression, so just one predictor variable and one outcome variable. And now we're getting to the main tool that we want to use, which is one outcome variable with potentially many predictor variables, so 5 or 10 or whatever. So you can think of multivariate regression as essentially fitting a plane of best fit. So it starts to complicate the way that we interpret the results, because we've got so many different dimensions when we add in lots of additional explanatory variables. So if you've got more than one independent variable, we might have our y, so our output variable, we might have our intercept a, and then we have our first beta value with the explanatory variable, so b1 and x1, plus the beta coefficient for 2, b2, and the second explanatory variable x2, and so on and so forth. Okay, so often you'll see equations for multiple regression written down like this, and it looks very scary, but it's exactly the same as you've already covered in the previous example, so don't be scared of that. So plant growth is a function of light intensity and the length of time. So maybe you have the level of plant growth as your y variable, and then you have x1 as the variable for light intensity, and x2 as the variable for the length of time that you let the plant grow. And these would be very good predictors, I suspect, for why you might also want to include temperature within there. Um, uh, uh, well, maybe not for, yes, you could include temperature and see what would happen. I would be inclined to use temperature because that's going to affect the rate of growth, given the fact that you're also including length of time. So you could leave something for a year, but if it's going to be 2 degrees Celsius, so what is that? That's 40 degrees Fahrenheit, then basically it might not grow very much. But if you included if you left it for 12 weeks, but you were growing at 30 degrees Celsius, which is what 90 degrees Fahrenheit, something like that, then you would expect a lot of plant growth, basically. Okay, so that gives you a bit of an example about what you can do here, and this is kind of how you should think about it. It does start to get a lot more complicated though as you add lots of variables in. So it's not something that you would go off and do by hand explicitly, and actually to do the calculations for some of these regressions when you add in lots of variables, that there's a lot going on behind the scenes. So we're not going to calculate multiple regression by hand within the laboratory, but we will do one using the built-in functions because it's the same kind of understanding that can be applied. So issues, yes, we're still using OLS, so ordinary least squares. So you might hear of that in papers or things that you read, textbooks, and often it's just abbreviated to this acronym. So you just want to be aware of that. So OLS, so the relationships are still expected to be linear, okay? And it's still regression, so you need a logical reason why you're including certain predictors. I mean, that's always the case, right? So you should look at theory before you build your model, and that theory, so that will be other papers that have been carried out. It might also be background literature for other empirical assessments on the topic that you're focusing on. And in there, it will give you some information as to how people who work in this area already think the world works. So maybe it's already hypothesized that plant growth is driven by length of time and light intensity and temperature. And therefore, that gives you the theoretical motivation when you do your study. Perhaps you're interested in testing fertilizer, the impact of fertilizer on plant growth. So there's an existing study which doesn't include fertilizer, which says these are the main factors of growth. And then what you're going to do is you're going to augment your regression by including a variable for the amount of fertilizer that you've applied to different plants, okay? So that's kind of why you need a logical reason to include your predictors here, and you can get that from theory and past empirical analyses. Comparing coefficients. So we need to be able to compare coefficients across metrics. Bigger coefficients aren't always necessarily better. Coefficients are scaled, so they're in the units of original measurement. So that's a tricky one to remember. So most of what we've done here has been focusing just on the absolute measures, but when you take the logarithm of metrics, maybe you need to correct because your data aren't normally distributed, then you need to think about how you interpret those results. And I don't think we're going to get to it in this course, but definitely you will read papers if you're looking at regression where people have decided to take the logarithm. And you need to recognize that you might need to take the anti-log in order to understand those values in absolute terms. Okay, so I think that's fairly straightforward. Coefficient validity. So if a coefficient fails its t-test, it doesn't necessarily mean it needs to leave the regression. Yes, it's complex. Okay, and yes, it's part of the art of stats. So for all of our rhetoric around quantitative methods being superior, it's how we do science, there is still an element of how we kind of build those models, we evaluate those models, because this is all based down on human intuition and the analyst. And then we have to make a decision about which model we're going to go with and which model we're going to explain and how that might lead to future theory. So there is a kind of hard quantitative statistical element, but then there's this kind of less kind of clear-cut route for how we then decide to interpret those results and then portray them in the literature. And that's why you get such great debates between different schools of thought about how we should interpret the world, because they might be using the same data or the same methods, but they might interpret those results in different ways, okay? And there's a lot of discussion in various different literature fields between people arguing on the nuances of how you interpret regression analysis. Great. So issues in multivariate regression, multicollinearity. So this is basically where you have strong correlation between independent variables. So you might want to look at correlation plots in advance in order to understand how you can pick variables which have a low level of correlation between them. So it can hurt the regression. The model can't assign the part of the variance that it's trying to an individual variable if all of the variables are varying at the same degree, because they're highly correlated. If adding variables causes the coefficient sign to change, multicollinearity may be a problem. So yeah, as I mentioned before, you can run a covariation table. So this might be something you do in advance. It might be something you do afterwards as a check, robustness check. But you need to be aware of this. Overfitting the model, always an issue. So no matter if a new independent variable is related to the dependent or not, the R-squared may increase. So if you put too many variables in the model as well, it can fit this noise improperly. So I mentioned before that we start to think about how we can penalize the model for having lots of variables, because we can get the R-squared value increasing. So therefore we look at the adjusted R-squared. But also I kind of explained about the need for us to have elegant, simple models. So that means having the least amount of explanatory variables that can explain the largest amount of data variance in our data. Okay, that's the holy grail. That's what we're looking for. And I gave you that really nice example of Newton's gravity model, which has three input variables and then a fourth gravitational constant. So I think that that's a really good example of how the world's a huge, complex, messy place. What we want in this case is want to reduce all of that complexity down to a very simple formula. And it always reminds me of Richard Feynman's comments. So Richard Feynman is a very eminent physicist who was out at Caltech, and Feynman would always say, you should have 30-second elevator pitch, and you should be able to explain what you do in that time to a 3-year-old, essentially, so a very young child. And many academics fail this. But it's kind of abstracting away all of that complexity from the kind of really hard part of understanding these complex statistical methods to just a very simple problem. Should you do this or should you do this in reality? What decision should someone in local government take regarding tax changes within the city of Fairfax, for example? And that's the type of thing that you might be using these models for. And you need to be able to reduce this down to a simple description of what the purpose of the research is, what the research question is, and what the conclusion should be based on that analysis. Okay, let's see what happens as we try to see how a dependent variable, e.g. tax burden, is predicted by adding independent variables. So at the moment we've got tax burden and we've got a predicting variable, and then we add in age and we add in population density. And essentially if we look at the F statistic, we've got 20 over here with an R-squared value of 30. We add in another variable, so the R-squared value starts to increase quite a bit. So let's look at the adjusted R-squared. So we've got 28% data variance over here for a single variable. We've got 37% data variance over here for 2 explanatory variables. and then we've got 36% data variable, sorry, 36% variance explained over here when we've got 3 data variables. So I think the key point is that by adding 1 variable, we can increase the amount of explanation that the model has, but it doesn't just continue linearly, because we actually need to adjust for the number of variables that we've got, and even if we add more, we look at the adjusted R-squared value, the amount of explanation that our model can provide might actually decrease as we add in lots more variables. So more isn't always better, that's my point. Okay, and this just emphasizes again the same kind of effect that's taking place. So that's the course, that's the end of the material. Let's just do a quick review. So I mentioned before that we were going to have a course date. So I've set this a course date for the exam. I've set this so far for December 13th. So that's going to finish on the Sunday, which normally we have coursework submitted around a Friday or a Sunday. It's the weekend time, based on your preference. So as a consequence, we will have this at the end of the reading week, essentially. And the test is going to be 2 hours in length. It's going to be cumulative, so it will pick up on things from earlier in the course. So you can maybe pick up some easy points there because you've already covered the material. But then it will also pick up on some of the things that we've done in the last few lectures. So that could be correlation, could be regression. There'll be 5 sections, so there will be calculations. That means that you need to be able to take the data, potentially run it through some R code and provide the answers. There will be some parts which just focus on short answers. There will be some parts that focus on fill in the blanks. There will be some parts that focus on multiple choice. In fact, I think maybe I'll just make multiple choice longer, so that the reason why I don't like filling the blanks is if you provide the right answer but you provide a spelling mistake, you might get the mark taken off you, and I think that's really unfair. So personally, I don't want to do that. So that's why. Okay, well, these are subject to change anyway, but this is going to give you kind of a good overview of what we're going to be doing within this, the exam. But I don't want you to get too stressed about this. You covered a lot of it. What I do want you to do is do the groundwork to prep, and we're going to just kind of cover some of those areas for us to help you think about what you should be focusing on. So just before we begin, I think that this course has given you a really strong background to help you develop as a person, and I'm really happy you've done it. Please do reach out to me again if you have questions, if you're interested in this area, because I'd love to hear from you. Do say hi to me if you see me around once we finally get back to campus. Yeah, you can connect with me on socials if you're interested, or you can email me if you've got any further questions. But it's been a real pleasure to teach you this term. I'm just sad that we couldn't do it in a classroom so that you can ask me questions and I can best help you. I've tried to help you to the best of my ability via email. I know it's not exactly the same, but I am adjusting the course marking criteria to be more favourable in your favour this term, because I feel like it's not been a good time for all of us, and I appreciate that, especially working remotely, it places a higher strain on you in terms of stress level and mental health. So I'm trying to reflect that within the marking criteria for this course. So what have we done? Well, we've covered the data terminology for different structures. We covered descriptive statistics, including spatial descriptive statistics. We've covered probability and probability distributions. We've covered how you do sampling, how you estimate population parameters. We've gone through that those 6 different steps for how you formally test and evaluate hypotheses. And we've gone over inferential statistics in quite a lot of detail. So we covered the issues with geographic data. So there's plenty, it's where do you draw the boundary? How does modifiable areal unit problem affect your results? How does spatial aggregation or ecological fallacy affect your interpretation of the results? And we've focused on different types of measurements of data. In descriptive statistics, we focused on central tendency, dispersion, shape. We focused on how we describe spatial statistics, so maybe we capture distance within that, within those basic descriptive statistics. And we've covered relative versus absolute measures of statistics. Within probability, we've focused on both discrete distributions and continuous distributions. So those discrete distributions that we focused on were those which have categorical outcomes potentially. So it might be binomial. So you've only got two possible outcomes. So success or fail, or true or false, or Poisson. So maybe we have a variety of different events which are all part of some sort of discrete outcome. And then we focused on continuous distributions, so that could be the normal distribution, and potentially how we then test z-scores and z-scores to understand how they relate to probability. And that fed forward then into how we do things like evaluate hypotheses. We covered sampling methods, so how we carry out sampling approaches, so whether it's random sampling, systematic sampling, stratified sampling, clustered sampling, or hybrid approaches, which might blend a variety of these different sampling approaches. We focused on the central limit theorem and how that informs our understanding for inferential testing. And we focused on confidence intervals, so how do we estimate the interval within which we think a population parameter may fall within, given a set of data that we've collected. Hypothesis testing, so this is obviously key. We've covered this week in, week out over the past 6 or 7 weeks since we covered this. So there's 6 steps: stating the null hypothesis where there's no effect, stating the alternative hypothesis where we think that there's some sort of effect and we want to basically see whether we can be a certain degree see whether we have a certain degree of confidence to test whether that's true or not. So we need to select the appropriate test, select the significance level, so our alpha. We need to delineate the regions of rejection and non-rejection from the null in the distribution, calculate the test statistic, and then once we've got that, we need to be able to make a decision regarding the null hypothesis. So that's either retaining the null hypothesis, so not having enough evidence to reject the null hypothesis, or we have a certain degree of confidence. Maybe we're 95% certain that there is an effect and that we can reject the null hypothesis. So I think the important thing to remember, of course, is that we can either reject or fail to reject the null hypothesis. Okay. Errors and p-values. So type 1 error is essentially rejecting the null when it's true, so that's seeing an effect where there isn't one. Type 2 error is failing to reject the null hypothesis when it's false, so that's failing to identify an effect when there is one. Type 1 errors obviously are important to us because we choose an alpha value, and this affects how we potentially fall into a type 1 error trap. And the test statistic that we obtain, the size of that's going to affect how likely we are to reject or the null hypothesis. So that's something which we need to be aware of. And I think you hopefully have a good understanding now of how we evaluate p-values. So normally at a 95% significance level, if we're looking for p-values that are below 0.05, and if that is the case, then we can be 95% sure that the results haven't just occurred by chance, and that we can reject the null hypothesis based on the evidence that we have. Inferential testing, so this is important. It's about being able to pick the right test for the right situation, and I know that's complicated, and I'm afraid you're going to just need to learn how to do those, how to pick the right tests in those right situations. So that's going to depend on how many samples, what kind of samples you've got, what the type of question is being asked, and you've got the textbook to understand that, or you can use the flowchart, the statistical flowchart for commonly used tests, which I've put up at the start of the lectures for many of the inferential parts of the course. And that gives you, a good way to start to think about the problem. So if you can try to understand that structure, then, in your mind, you'll be able to evaluate what you should or shouldn't do in a certain context. So one sample tests, we've covered a lot of these. So it's how do we evaluate one sample difference of means, one sample difference of proportions. Okay, two sample tests. So again, quite similar, we're evaluating difference of means. We're also evaluating matched pairs, t-tests, Wilcoxon rank sum. So these are our parametric approaches and non-parametric approaches. And we also evaluated two sample difference of proportions. Multiple sample tests, so we focus on ANOVA, and we also focus, so that's our parametric approach, and we also focused on our non-parametric approach, which was the Kruskal-Wallis test. So you've got all the code for this for the laboratory sessions, so hopefully you can look back on that if you need to. Categorical difference tests, we looked at the chi-squared goodness of fit test, so maybe if we're focusing on categorical data. And then if we want to evaluate whether data are normally distributed, we've got the Kolmogorov-Smirnov goodness of fit test, and the Shapiro test, Shapiro-Wilks test for normality, for us to actually carry that out in R. And then we've got contingency analysis as well. And then, as we've covered in the last couple of weeks, got correlation, so we can test parametric data using a Pearson correlation approach, or we could test non-parametric data with a Spearman-Rank correlation approach. And we did some inferential spatial statistics, so we focused there on nearest neighbor analysis, so using point patterns, as well as focusing on quadrat analysis, and then focusing on polygons, so focusing on the join counts between those spatial areas, and then also focusing on Moran's eye, so understanding if there's some sort of spatial autocorrelation effect within the data that we've got, and whether we need to change maybe some of the statistical approaches that we were thinking of using based on that level of spatial autocorrelation. So the hint is I won't make you do calculations of any of these tests actually in the class, but there will be questions. Regression, bivariate regression. So does a variable x actually account for a significant proportion of an output variable, dependent variable y? And also, can we introduce more than one predictor variable into that type of approach? So a multivariate regression approach, and we will cover this in the laboratory session, which is next. The important thing, obviously, is to be able to plot the residuals and check whether we're actually meeting the assumptions required for these regression approaches. Okay, great. So that's just a roundup of the course. I hope that was useful for you. There will be more information from me on how I'm going to review the criteria for the course for marking, to make it a bit more lenient to reflect the challenges that you've had as remote learners this term as a result of the pandemic. And I'm empathetic to the situation which you've been in, so I hope to reflect the marking structure in that. And I will do that also for the number of assignments that you use to calculate that proportion of the mark. So I will allow you to drop certain assignments, a certain number of assignments, and allow you to pick the best number of assignments with the highest scores, in essence. So reach out to me if you've got any questions. It's been a real pleasure working with you this term. I hope that you found this lecture interesting. As I say, I think this is one of my favourite out of all of the course. Yes, it's more advanced material, but it's also the place where this is going to be a great bedrock for your future in this statistical area. Okay, thank you very much. Nice to see you, and I'll see you in the laboratory session. Goodbye.